So before we go on to our next type of reaction with the carbohydrates, I want to pause for a moment and go back to something that is very kind of neat in the lab to actually see. And it is traditionally a qualitative test that we can do to make sure if something is an aldehyde or a ketone or really a sugar, because we're talking about sugar chemistry here, right? And this thing is called the Tollens reagent. And Tollens reagent is very well known both to the college environment, to the high school environment, and even down into the actual elementary school environment, because using a Tollens reagent is very neat, especially when you're showing it to kind of young kids at the same time. So the good news is that you will probably see the Tollens reagent in the laboratory at some point in this semester. So you won't go shunned. You will see the Tollens reagent actually in motion and begin to see what it will actually do. So let's talk about it for a minute and let's discuss what this Tollens reagent is all about. Now, the Tollens reagent is going to fall under the whole concept of oxidation, and that's kind of where we ended up, right? I mean, we talked about this reduction, we've talked about this oxidation, and I want to finish the oxidation section by talking about the Tollens reagent. In the previous video, we said that we have two reagents that undergo oxidation, or that make these carbohydrates undergo oxidation, and that was liquid bromine, and that was a qualitative test. We took bromine, we dropped it into a test tube. If the color disappeared, then oxidation was going on. If the bromine color stayed in solution, then oxidation was not going on, and this was a sign that we didn't have a carbohydrate at all. Okay, so we talked about bromine, we talked about nitric acid, and we talked about nitric acid doing oxidation and it actually targeting the top and the bottom of the carbohydrate molecule. So it did the head and the tail both. Very powerful as far as the oxidation is concerned. And this is what ended up with aldonic acids as far as bromine goes and alderic acids as far as nitric goes, right? So let's do a summary here. Let's just kind of recap what we've discussed. I can take bromine and put this in a test tube with a carbohydrate. And this thing will oxidize. And what it will oxidize into is a aldonic acid. So we have a C double bond OH group up here at the top, and then who knows what we have in the backbone, it doesn't really matter, and then CH2OH at the bottom. So what bromine did is we didn't look at the mechanism. That was good, right? We didn't focus on the mechanism at all. But bromine takes a look at this top aldehyde group and it erases this hydrogen and it puts an OH group here instead. And this was by definition oxidation. We are increasing the number of C to O bonds. We first started out with a carbon double bonded to an O, and now we end up with a carbon double bonded to an O and a carbon also bonded to another oxygen. So we've increased the number of C to O bonds. So that was the purpose of bromine. This was called an aldonic acid. We also talked about nitric acid in the previous video. And if we take nitric acid and add it to a carbohydrate, what we see form is something called an alderic acid. And just like before, we have an aldehyde group, who cares what's in the center, and then a CH2OH group down below. Well, nitric, well, it does the same thing that bromine does. It targets the head and it converts that to an OH group. And then nitric also targets the CH2OH group down at the bottom. And what it turns this into is not a CH2OH now, but another C double bond OOH group. So we get two groups, two carboxylic acid groups. There are two groups on the molecule, therefore this thing is called an aldaric acid. There are two groups, right? Okay, well, the Tollens is another oxidation reaction that we can talk about. The problem is that bromine and nitric acid, these really work well only with aldoses. That's where we see them. Ketoses, we don't really see these reactions happen. So these are really focused on aldoses. The aldoses undergo a reaction with bromine. The aldoses undergo a reaction with nitric acid. If I gave you a ketose and I said what would happen if you took this ketose and reacted it with nitric, or this ketose and reacted it with bromine, you would tell me nothing, right? So ketoses don't do anything as far as these reactions go. Aldoses do, however. Well, the nice thing about tollens is that tollens will basically make an oxidation reaction go forward with aldoses or ketoses. It really doesn't matter. Both of these work here. So that's the nice thing about the tollens. Both aldoses and ketoses are oxidized. Now, what do they oxidize into? That's the question. What type of product do we form? And what's so special about the Tollens reagent? Exactly what is the Tollens reagent? Okay, well, let's kind of start there first. The Tollens reagent is a mixture of a base. So we're going to have some OH involved in the actual reagent itself. And we're going to kind of increase that base a little bit, and we're going to put some ammonia in there as well. And this reagent is also going to include silver, and it's the silver ion. It's silver plus, right? Silver comes to us in the form of +1 most of the time, and it's this +1 silver that basically will give us this positive readout of a qualitative test. Now, does the silver get incorporated in the actual product? The answer is no, but the silver allows us to determine if a reaction is going forward or not. So the Tollens reagent, it's a reagent, and it's whether, or we use it to determine whether a known carbonyl compound is an aldehyde or ketone mainly. But because we're talking about aldehydes and ketones as far as the sugars go, these have aldehyde and ketone groups, so we should be able to use the Tollens reagent in order to do that as well. We call this ammoniacal silver nitrate solution. So let me spell that out for you. Ammoniacal, A-M-M-O-N-I-A, ammonia, right? We can kind of see why ammonia is involved, NH3. Silver, well, we know that silver has to be involved. Where do we get the silver from? We've got to get the silver ion from somewhere. We get it from a salt, and that salt is silver nitrate. So we are going to take some silver nitrate, and we're going to make a solution of it in a basic environment. And what happens is that this complex begins to get formed. So really what goes on if we want to prepare the Tollens reagent on our own, it's very easy to do. We take silver nitrate. This is a very shiny crystal, a very small jar. We're talking like 5 grams of this silver nitrate. Currently, the value of a 5-gram sample is about $100 and some a piece. So this is slightly expensive, but you don't need that much of it, which is the nice thing to make this reaction go forward. So we're going to take this silver nitrate, and what happens is that we add some ammonia hydroxide to it. So bottom line, the reagent, I can't just order Tollens reagent. This thing is not really stable as far as shelf life is concerned. Most of the time it has to be freshly prepared, so you kind of want to make it as you need it. So this preparation requires 2 steps. We take sodium hydroxide and silver nitrate, and we take a few drops of dilute sodium hydroxide. We add it to an aqueous solution of silver nitrate, and what goes on is that a reaction happens, and we get this Ag2O, and we get sodium nitrate, and we get a little bit of water. Okay, so then what will happen is that we play off of this Ag2O. So Ag2O, and then we add ammonia to it. So in the next step, what happens is that aqueous ammonia is added until the silver oxide is dissolved. This silver oxide will be kind of a brownish precipitate when it forms. So we'll take this brown precipitate, we'll redissolve it back in solution using ammonia. And at that point, it kind of clears up, and you have a crystal clear solution, and we get this complex. And this complex is going to be a silver NH3 2 complex, right? So this thing is going to carry a charge with it. And that's the main component of the Tollens reagent. Now, will I ask you something like this on the test? And the answer is no. I'm basically providing you this information for just your general knowledge of what's going on with the Tollens. Why is it so special? What's kind of the weird and strange chemistry that goes on with it? I said that this thing is a short shelf life, right? So there's a story with the Tollens reagent that I could tell you. Very often, in our lab at least, we have a box of silver nitrate that had been ordered years and years ago. The expiration date had been expired for 20 years probably, and we had always been using the silver nitrate to make our Tollens reagent. So we would make this Tollens reagent, and we would set it on the shelf, and this bottle would actually stay on the shelf for a year or two before we would have to make more, and we never really had a problem out of it. And it always gave us a positive read when it should have gave us a positive read. The problem with the Tollens reagent, however, is that we ran out of the old expired stuff recently, and we ordered new silver nitrate to actually make the Tollens reagent with. When we got this new bottle of silver nitrate, we made our Tollens reagent fresh, and we set it in the bottle. It's a glass bottle with a lid, and we basically set it down on the shelf, and people were using it, and we had no problems with it. However, about the midway through the semester, about the end of the semester, what happened is that we went to go and we picked up the bottle of Tollens reagent, and when we did that, the Tollens reagent glass bottle, very thick wall piece of glass, actually exploded in the hands of the person that picked it up. And when this bottle exploded, silver nitrate went everywhere. It went all over the lab bench, it went all over the lab tech, it went all over a student. Silver nitrate was horrendous to try to clean up. And not only that, but your experience with silver nitrate also shows that when you get it on yourself, you're going to start to stain as well, and you begin to freckle into brown spots wherever the silver nitrate touches. So that's kind of the take-home message of the Tollens reagent. Tollens reagent is not very stable. When you let it sit, it can become explosive, and the force of that explosion was so strong that it actually completely blew up a very thick wall piece of glass container that it was in, and it went everywhere. So just be really careful with the Tollens reagent. You know, when you handle it, when you use it, just make sure that you're treating it the right way, or it will let you know if you've abused it. Okay, so what's the nice thing about the Tollens reagent, you know, other than the chemistry? Well, what goes on here is that if we have a ketose or if we have an aldose, so a ketose or a aldose, and we add Tollens reagent to it, most of the time we do this in a test tube. And we want to know if is this structure really a carbohydrate or not. This test tube will let you know if the solution that you have has a ketose or aldehyde group. And what will happen is that the silver precipitates out. So the silver precipitates, and it begins to form a layer on the test tube itself. And we actually make homemade mirrors by using the Tollens reagent. So a couple of drops of carbohydrate, a couple of drops of the Tollens reagent, shake it up in the test tube. The reaction takes a couple of seconds at least, and then the more you shake it, eventually that silver is going to precipitate out. It latches onto the sides of the piece of glass or the container that you put it in, and you get this nice mirrored reflection all the way around that you can see yourself in. So beautiful, kind of nice little chemistry or nice reaction that goes on. The ketose or the aldehyde, basically you end up with, up here at the very top, a C double bond O O, and there's an O minus. So that's kind of the ending result that we see.